This is Hair-Reverse, a mysterious signal, a puzzling trajectory, and a meeting point near Jupiter that should not be this precise. If you want more stories like this, hit like, subscribe, and share. Your support truly helps. Thank you for being here. Now, let's follow the evidence. Natural objects from interstellar space follow a familiar pattern. They enter the solar system on steep, fast paths. Their trajectories bend under the gravity of the sun and planets, and then they depart again. They can brighten and fade as sunlight warms their surfaces, and they can drift slightly if jets of gas leak from heated ice. But they do not normally behave as though they can select a target and adjust their speed to reach it. 3I Atlas is framed in the sample as an interstellar visitor that appears to do exactly that, not through loud displays or obvious exhaust, but through a quiet sequence of changes that look purposeful when set against the usual rules. The first scientific anchor is non-gravitational acceleration. Astronomers measure a moving target against background stars and fit an orbit that predicts where the target should appear on future nights. If gravity alone shapes the motion, those predictions tighten as observations accumulate. When the target persistently arrives a little off the expected track, the leftover is treated as a real effect and folded into the model. In comet science, the most common cause is outgassing. Sunlight warms volatile material, gas escapes, and the recoil produces a small thrust. This is ordinary enough that the term itself carries no implication of engineering. What matters in the sample is the way the effect is described. The acceleration is presented as coherent rather than random, and as continuing in a way that resembles tuning rather than simple heating. Many comets show their strongest activity near their closest approach to the sun, then gradually quiet down as they recede. Continued activity farther out is possible, especially if the body contains very volatile ices or if its structure traps gas and releases it later. But the direction and stability of the push become the deciding details. A sustained push in a consistent direction can move an object's future position by enormous distances over time, and small changes can accumulate into a close approach that would not otherwise happen. The sample builds its tension on that idea. Small corrections, maintained long enough, can look like targeting. The second anchor is chemical, drawn from spectroscopy. Spectroscopy separates light into its component colors and reveals patterns that correspond to elements and molecules. Those patterns can be measured even when the object is too small to resolve as anything more than a point of light. The sample claims that nickel stands out compared with iron, and it treats this as an industrial hint. In nature, nickel and iron often appear together because they're forged in similar stellar processes, and they commonly mix in rocks and metal-rich bodies. A nickel-heavy signal without a matching iron context would be unusual, but unusual does not automatically mean artificial. The spectrum can be influenced by dust surrounding the object, by gas excited by sunlight, by surface coatings, and by the limits of measurement itself. Instrument sensitivity, calibration, and the changing geometry between Earth, the object, and the sun can all reshape what the spectrum seems to say. The sample leans toward the idea that nickel without a matching iron context hints at processing, but the documentary keeps the claim in its proper place, a compelling anomaly that requires replication across instruments and teams before it can support anything larger. The third anchor is geometry, and it brings Jupiter into focus. The sample centers on Jupiter's Hill sphere, a concept from celestial mechanics that describes the region where a planet's gravity dominates local motion more than the sun does. It is a useful boundary for capture calculations. The sample places that boundary at roughly 53.5 million kilometers and claims 3I Atlas crosses at roughly 53.6 million kilometers, making the pass uncomfortably close to the implied line. This kind of number creates a strong impression because it suggests a controlled approach to a specific threshold. Yet even here, care is needed. The Hill sphere is not an edge that can be scraped. It is a region, and the exact value depends on assumptions and on how the boundary is defined for a given problem. Still, the sample uses it as a marker for something more important, the point where the story shifts from a solar orbit problem to a Jovian system problem. That shift matters because capture is difficult for a fast interstellar visitor. In a simple gravitational flyby, Jupiter curves the path, but the visitor leaves again, carrying essentially the same speed relative to Jupiter that it had when it arrived, only redirected. To become a bound satellite, the visitor must lose energy during the encounter. Nature has ways to take energy away, but each way is constrained. A direct collision would do it, but that ends in destruction. A close pass that exchanges energy with a moon can do it, but the alignment must be extraordinarily specific. Fragmentation can change the outcome, but fragments still obey the same underlying energy rules unless something else removes speed. That is why the sample returns again and again to breaking, because breaking is the missing mechanism when stable capture is implied. The sample attaches a timetable to the problem by pointing to March 17, 2026 and describing a close pass near a small, irregular moon soon after the Hill-sphere crossing. The moon name in the sample appears as Uimi, and the surrounding wording shifts enough to suggest transcription uncertainty, but the category is clear. The irregular moons of Jupiter are small, distant, and often on retrograde paths, meaning they orbit opposite to Jupiter's rotation. They are faint targets, difficult to image sharply, and easy to leave as anonymous points in the background of larger missions. The sample treats that obscurity as part of the mystery, because a meeting in a poorly imaged region would be hard to audit in public. It also treats the Ananke group as especially strange, because retrograde groups are often interpreted as remnants of past captures and collisions, and their orbits are dynamically distinct from the orderly paths of the major moons. If an interstellar object were to thread into that neighborhood with precision, the question would not simply be how it got captured, but why it would choose a place defined by backward motion and limited visibility. The sample adds one more observational detail to support the unease. The light curve suggests a surface with a persistent sheen. Light curves can imply rotation rate, tumbling, and gross shape, and a reflective surface can sharpen the variations. But reflectivity can also be produced by fresh ice, by dust grain properties, and by viewing geometry that briefly favors strong glints. The point is not that a metallic look proves metal, but that the sample treats the look and the motion as converging hints, each weak alone and stronger together. The final element introduced early is not physical at all, but procedural. The sample claims that information is handled under national security protocols associated with the year 1947, with an implication that unusual restrictions surround imagery and orbital detail. Those claims are unverified within the sample, and there are ordinary reasons public data can be limited, including telescope scheduling, proprietary observing windows, and the plain difficulty of imaging a faint, moving target. Yet the feeling of restriction has its own effect. It turns the lack of clarity into part of the evidence, because uncertainty can be interpreted as concealment. Section 1 ends with a narrow question that stays within the data. Will 3I Atlas lose enough speed near Jupiter to remain bound? And will its path toward the irregular moons continue to look deliberate as the measurements sharpen? The approach toward mid-March 2026 becomes a timing problem before it becomes a mystery problem. Every new night of tracking refines an orbit, and an orbit is not just a curve in space, but a schedule. It predicts where 3I Atlas should appear, how bright it should be, how quickly it should move against background stars, and how its path should bend as it enters the region where Jupiter starts to matter. The sample frames March 17th as the date when the object reaches a close pass with a small, irregular moon, while already deep in Jupiter's sphere of influence. That makes the days leading into it unusually tense, because the closer the object gets, the less room there is for ambiguity to hide. A drifting comet can be explained away while it is far and faint. A candidate capture event tightens the constraints. Either the object continues on a clean, hyperbolic exit, or it starts to behave like a satellite. There are intermediate cases, temporary captures, and looping trajectories that last for weeks or months. But even those are visible in the geometry once enough observations exist. In practice, teams rely on services like the Minor Planet Center and orbital solutions maintained by groups that specialize in astrometry, and they compare independent fits. If the object keeps slipping off the purely gravitational prediction, the non-gravitational terms become part of the forecast. That does not make the object artificial. It simply means that the observer's model needs an extra push. What the sample insists on is that the push is not merely present, but unusually well aimed in a way that aligns with a very specific outcome near Jupiter. This is where the narrative turns from a curiosity about a strange visitor into a claim about a meeting. Even within a conservative scientific frame, a meeting is a legitimate question, because Jupiter is not empty space. It is surrounded by a crowded system of moons, rings, faint dust, and irregular bodies that exist on orbits shaped by a long history of capture and collision. If 3I Atlas threads that environment, the encounter is not just between an object and a planet, but between an object and a whole moving swarm. A close approach to any moon is not only a point of interest, It is a gravitational event that can slightly reshape the visitor's energy. That is why timing matters. A near pass at the right moment can exchange energy in the three-body dance between the Sun, Jupiter, and the Moon. Under extremely specific conditions, that exchange can reduce the visitor's speed relative to Jupiter enough to create a bound orbit. The key word is specific. Most flybys increase complexity without producing capture. The object arrives too fast. The alignment is wrong. The encounter geometry does not pull energy out, and the object leaves. The sample's tension comes from the suggestion that this time the geometry is not merely favorable, but precise enough to feel chosen. That claim hinges on what the orbit solutions show as the date approaches. Precision does not mean certainty, because precision can be an illusion created by underestimating uncertainty. Small forces can masquerade as stable behavior over short arcs of observation, then drift as more data arrives. And the environment near Jupiter is full of subtle influences. Solar radiation pressure can affect very small bodies. Outgassing can change with rotation, producing thrust that varies over a day. A fragmenting nucleus can alter the center of light used for measurements, making the astrometry appear to wander. Even the background star catalog used for reference can introduce systematic bias. Any one of these could create the appearance of targeted motion if the observer expects a target. The sample challenges that caution by leaning on a practical point. As the object approaches Jupiter, the required corrections to hit a narrow passage grow harder to hide inside ordinary uncertainty. A small bias can explain a small miss. It struggles to explain a consistently narrowing miss that collapses into a close approach at a specific time and place. The documentary tone stays balanced here. It treats the approaching date as a test that will either relieve the anomaly or deepen it. If the visitor reaches the predicted region without additional unexpected pushes, and if its path remains consistent across observatories, then the idea of deliberate aiming becomes harder to dismiss as pure pattern seeking. If the orbit keeps shifting and the close pass timing slips, then the drama may be an artifact of early fits and limited data. The sample also anchors its suspense to the idea that the object is aiming not at Jupiter's main moons, which are heavily studied, but at a small member of a retrograde cluster. That emphasis matters because the irregular moons are difficult targets for direct imaging. They are faint, and their orbits carry them far from Jupiter's bright glare, which complicates observations from Earth. Space telescopes can help because they avoid atmospheric blur, but they still face the limits of distance and brightness. Even if the moon itself remains a weak point of light, its orbit is well enough known to predict close approaches between bodies, and a close approach can be inferred from the visitor's track alone. This is one reason the March window becomes so important. It is not only about a dramatic image. It is about whether the visitor's motion shows the gravitational signature of a near encounter, and whether its speed relative to Jupiter decreases in a way consistent with capture. Those are measurable outcomes even in the absence of a perfect photograph. The sample adds chemical and reflective hints that become more actionable as the object brightens. Spectroscopy improves with signal, and signal improves as distance shrinks and geometry brightens. Major observatories, including facilities used by NASA and ESA partners, can schedule follow-up that compares visible and infrared signatures to see whether the surface composition changes as it nears Jupiter. That matters because a natural outgassing model often predicts changes, new jets as sunlight heats different areas, evolving dust production, and shifts in the measured spectrum as gas and dust fill the near environment. A propulsion hypothesis, in contrast, would predict patterns that may not follow simple solar heating, such as thrust that persists when it should fade, or thrust that aligns with navigational needs rather than thermal exposure. The documentary keeps the claim at the level of expectation rather than conclusion. If the acceleration aligns with sunlight, that is ordinary comet behavior. If the acceleration aligns with the desired turn near Jupiter, even when sunlight cannot easily account for it, the anomaly deepens. The sample's insistence on a braking problem returns here because Jupiter capture is unforgiving. For a visitor arriving from outside the solar system, the speed relative to the Sun is already high, and the speed relative to Jupiter can be higher still depending on approach direction. Jupiter can bend the path, but it cannot by itself remove energy. Energy removal requires either a dissipative process or an exchange with another body. If 3I Atlas becomes bound, something must account for that energy difference. The sample suggests a quiet mechanism, not a dramatic plume, not a bright flare, but a ghost-like adjustment. That kind of claim is dangerous precisely because it is hard to falsify without detailed, shared data. It makes the procedural question, the question of what data is released and when, part of the scientific story. The documentary does not assume a hidden hand. It simply notes that restricted visibility, whatever the reason, creates a vacuum in which the anomaly grows. As March approaches, the narrative turns into an observational countdown, but not the loud kind. It is the quiet kind, where each updated ephemeris is a small revelation, each new set of residuals a hint of whether the orbit is settling into ordinary dynamics or resisting them. If the track tightens and the predicted close pass remains, the sample's idea of a rendezvous gains weight. If the track loosens and the predicted meeting drifts, the story changes again. Not into dismissal, but into a different sort of mystery. Why the early solutions pointed so strongly toward a place they could not hold. In either case, the mid-March window functions as a hinge. It is the point where the object's behavior must become legible, because the solar system does not offer many opportunities for an interstellar visitor to appear to slow down at the doorstep of Jupiter without leaving a trace in its own motion. Jupiter's Hill sphere is not a wall and not even a perfect sphere, but it is a practical way to describe why the sample treats the approach of 3-eye Atlas as more than a routine flyby. In celestial mechanics, the Hill sphere is the region around a planet where the planet's gravity can dominate the motion of a small body more than the sun's gravity does, in the sense that stable orbits around the planet become possible. The boundary is soft because the sun never stops pulling, and because other bodies in the solar system add their own small tugs. So the phrase is best understood as a zone rather than an edge. Still, the sample uses it as a threshold, because once an object moves deep enough into that zone, Jupiter begins to shape the future in a way that the sun alone cannot. The sample places that threshold at roughly 53.5 million kilometers from Jupiter and describes the object as crossing near 53.6 million kilometers, as if it is running a fingertip along a line that should not be that neat. Even allowing for uncertainty in the exact value, the message is clear. The path is presented as unusually close to the transition between solar dominance and Jovian dominance. What makes any claim about precision meaningful is the way astronomers derive a trajectory. Telescopes record the object's position against background stars. Those measurements are tied to star catalogs and corrected for effects such as atmospheric blur, instrument distortion, and the motion of Earth during the exposure. Analysts then integrate the motion forward and backward under the gravity of the Sun and planets. When the target moves toward Jupiter, the calculation can include Jupiter's largest moons as well, because their gravity is enough to matter at close ranges, and because their positions are well known. On top of gravity, models can include small corrections such as solar radiation pressure, which is the push of sunlight, and non-gravitational acceleration, which is the catch-all term for thrust-like effects caused by things like outgassing. None of this requires a special explanation. It is how modern orbit fitting is done for comets, asteroids, and newly discovered objects. The question becomes sharper when the residuals, the small differences between prediction and observation, do not behave like noise. If those residuals line up in a consistent direction and persist even as new observations come in, then the solution begins to imply a real force, not a measurement mistake. The sample translates that corridor into a margin of error on the order of 0.1%. Orbit analysts usually speak in uncertainty ranges rather than percentages, but the underlying question is clear. Do independent solutions converge on a narrow set of closest approach times and distances, and does that convergence persist as the observation arc lengthens? Early predictions can look tight and then loosen, especially if the object's brightness varies or if the center of light shifts as gas and dust change around it. Early predictions can also look loose and then tighten as more observatories report positions and the fit settles. The tension in the sample comes from the suggestion that the fit is not drifting into vagueness, but tightening into a specific geometry. Not merely toward Jupiter, but toward a particular part of Jupiter's domain. That matters because inside the Hill sphere, the object is no longer a distant visitor passing the Sun. It is a body threading a moving gravitational system. Jupiter is surrounded by dozens of moons on a range of orbits, and each of those moons is itself a potential partner in a three-body exchange. A three-body exchange is the plain idea that energy can be shifted between bodies when the geometry is right. In a simple two-body encounter, gravity bends a path but does not remove orbital energy. In a three-body setting, energy can be traded, leaving one body a little slower and another a little faster without any engine at all. The Hill sphere matters because it is the arena where that kind of trade becomes possible. But possible does not mean likely. The Hill sphere frames the deeper problem of capture. Crossing into Jupiter's domain does not capture an object. Many bodies pass through and depart again. In a simple two-body encounter, gravity redirects motion but does not remove orbital energy. For an interstellar visitor, the speed relative to Jupiter is typically too high for a stable orbit, unless something removes energy at the right moment. Nature has mechanisms, but each is constrained. A direct collision removes energy, but ends the story. Atmospheric drag is irrelevant at these distances. Fragmentation can change how the object responds to sunlight, and outgassing can produce a push, but both must still fit the timing implied by a capture. This is why the sample returns to the image of braking. It is not merely that the object changes course, it is that the course change is paired with the idea of arriving slow enough to stay. The Hill sphere becomes the place where the bookkeeping can be tested, because the post-encounter orbit will reveal whether the visitor kept its energy or lost some of it. This is why the irregular moons gain narrative weight in the sample. The Ananke group is a collection of small, distant satellites on retrograde orbits, meaning they move opposite to Jupiter's rotation. Retrograde groups are commonly interpreted as captured bodies or fragments of captured bodies, survivors of ancient disruptions that share similar orbital properties. They are faint, and many remain poorly imaged compared with the inner moons, not because anyone refuses to look, but because distance and brightness impose limits. Even so, their orbits are tracked, and their positions can be predicted. A close approach between a visitor and one of these moons does not require a sharp photograph to be real. It can be inferred from the visitor's trajectory and from the moon's ephemeris, and it can show up as a subtle kink in the visitor's motion. The sample describes 3I Atlas as aiming into that obscure neighborhood, rather than toward the famous moons that draw constant attention. This is where the documentary tone stays careful. A choice of neighborhood could still be coincidence, and coincidence becomes more likely when there are many moons to choose from. But the sample is not describing a random close pass. It is describing a passage that arrives at a specific time, near a specific moon, soon after the object crosses into the zone where capture could occur. That pairing of timing and place is what makes the Hill sphere feel like a checkpoint rather than a backdrop. A disciplined documentary voice keeps a conservative counterweight in view. Observation is biased. Surveys discover objects where they look, and objects are detected more easily when geometry makes them brighter. A path that seems finely tuned after the fact can be the path that made discovery possible in the first place. The Hill sphere radius itself is also an approximation used for intuition, not a physical rim that can be grazed. Even so, the energy ledger remains decisive. If 3I Atlas is slowing in the Jovian encounter, the loss must appear in its motion afterward. If it departs on a clear, outbound track, then the encounter is a flyby, and the story returns to composition and non-gravitational acceleration without the added claim of capture. If it emerges looping, lingering, or bound, then the story changes in a measurable way. A bound object will return, and its sky motion will shift from a one-time sweep to a repeating pattern tied to Jupiter. That is the quiet test implied by the sample. The Hill sphere is not proof of intent. It is the stage where intent, if it exists, must leave a signature that gravity alone struggles to mimic. Stable capture is a problem of energy, and that is why the sample keeps returning to one unsettling idea. An interstellar object arrives too fast to remain with Jupiter unless something removes speed at exactly the right time. A visitor from outside the solar system approaches on a hyperbolic path, meaning it is not gravitationally bound and carries excess energy that will take it back out again. Jupiter can bend the path and redirect it, but a redirected escape is still an escape. For 3I Atlas to become a moon in any meaningful sense, its speed relative to Jupiter has to drop enough that the path closes into a Jupiter-centered orbit rather than opening back out to the wider solar system. The natural routes for losing energy are well known, and each would leave a different trace. The simplest is collision. A body that strikes Jupiter or one of its moons becomes bound only by being destroyed, leaving debris, scars, and in many cases, a brief, bright event. The sample is not describing an impact, but an intact visitor that continues onward. Drag through an atmosphere is another way to dump energy, but it demands a plunge into the upper air. Near Jupiter, that would mean intense heating, rapid fragmentation, and a signature that would be difficult to miss, even at great distance. Fragmentation in space can also change an orbit by altering the way outgassing behaves, and by shifting the center of light used in measurements. But fragmentation does not automatically create a stable orbit, unless it happens in a very particular way during the brief window when Jupiter can trap what remains. The more delicate natural route is gravitational exchange in a three-body encounter. Jupiter is not a single mass in an empty field. It is a moving system of moons, and a visitor can trade energy with those moons if the geometry is just right. In that case, the visitor loses speed relative to Jupiter, while a moon gains a minute amount, too small to notice directly in the moon's orbit. This is the same physical principle behind gravity assists used by spacecraft, and it can happen naturally. It also explains why temporary captures exist, cases where a small body loops around Jupiter for a time before later encounters and the sun's pull allow it to escape again. None of this requires propulsion, but it does require timing so precise that it rarely happens for a body arriving from interstellar space at high speed. This is where the sample's attention to a tiny retrograde moon becomes consequential. The name of the moon is rendered inconsistently, but the idea is clear. Soon after crossing into Jupiter's domain, the visitor passes close to a small irregular body in the Ananke group, a population that orbits backwards. Retrograde motion matters because it changes encounter speeds. When motions oppose each other, relative speed rises, and higher relative speed generally reduces the time gravity has to work. That tends to make a gentle capture by a simple close pass harder, not easier, which is why the sample treats the approach as more than a lucky drift. If the visitor nevertheless threads a close passage at the right place and time, the encounter becomes a narrow gate. Either the geometry trades enough energy to slow the visitor, or it does not. Non-gravitational acceleration is the other lever the sample relies on, and it is already part of normal comet science. Comets often deviate from purely gravitational motion because outgassing produces recoil. Sunlight warms volatile material, gas escapes, and the object experiences a small thrust. Over weeks and months, even weak thrust can shift a trajectory by millions of kilometers, turning a wide miss into a close approach. In that sense, outgassing can make an object look as if it is aiming. Yet steering is not braking. A gentle push acting for months can place the visitor on the right corridor, but capture demands that enough energy be removed relative to Jupiter during a narrow window near closest passage. For that to happen, thrust must point opposite the visitor's motion in Jupiter's frame at the right time, not merely push in some direction that happens to change the track on the sky. If thrust is strong enough to matter near Jupiter, it should leave fingerprints. Dust and gas should brighten the coma, shift color, and alter the spectrum as fresh material appears. If the sample is right that the adjustment is ghostly, then the problem becomes sharper. A force big enough to slow an interstellar visitor should be hard to hide, yet the claimed hiding is part of the mystery. The sample's composition hints complicate the interpretation without resolving it. A reported nickel-heavy signal, alongside a reflective light curve, is treated as unusual, and unusual composition can change how activity looks. A denser crust can store heat, trap volatiles, and vent through narrow channels, producing thrust that is harder to recognize as a classic dusty comet. At the same time, spectra can be ambiguous when the target is faint and moving, and reflectivity can come from fresh ice or from grain properties that produce sharp glints at certain viewing angles. The documentary stance holds both possibilities at once. The measurements may be pointing toward an odd natural object, or they may be hinting at structure that does not fit the simplest comet picture. This is where real observing frameworks become the quiet center of the story. Repeated astrometry from multiple observatories can show whether the non-gravitational acceleration persists and whether it changes direction in a way that matches sunlight-driven outgassing. Spectroscopy from major facilities can test whether the claimed nickel signature repeats and whether other lines appear as the object brightens. Space-based instruments can reduce atmospheric noise and probe infrared features that are difficult to measure from the ground, helping to separate dust behavior from gas behavior and to check whether activity continues when illumination should be weak. None of these tools can read intention, but together, they can show whether the motion can be explained by ordinary processes without stretching them past credibility. Avi Loeb appears in the sample as a voice willing to argue that stable capture of an interstellar object is so unlikely that propulsion has to be considered if it happens. The documentary stance holds that as conditional. Capture first, mechanism second. If the post-encounter orbit shows binding, the energy change can be estimated from the fitted trajectory and compared with what a small moon could plausibly provide through gravitational exchange and what measured outgassing could supply through recoil during the encounter window. If the numbers do not close, the story moves into stranger territory, not because strangeness is desired, but because the accounting demands an extra term. The mid-March window therefore becomes a test rather than a prediction. After closest passage, 3I Atlas either continues outward on a clear escape trajectory, or it lingers on a Jupiter-centered path, whether for a short time or longer. If it lingers, the need to explain how it shed energy becomes unavoidable, and the focus shifts from what it is made of to what it can do.
If it departs, the capture claim fades, but the sample's narrower puzzle remains. Why a visitor from another star seems to make small course corrections that line up with a specific meeting in one of the least observed corners of the Jovian system. The sample places unusual weight on chemistry, specifically on a spectroscopic hint that 3I Atlas carries an abnormally strong nickel signature compared with iron. Chemistry in this context is not a sample in a laboratory. It is an inference drawn from light. A telescope collects photons reflected from the object's surface and photons emitted or scattered by gas and dust around it. That light is split into a spectrum, and within that spectrum appear patterns associated with particular atoms, ions, or molecules. Interpreting those patterns is careful work because the signal is faint and because the object is moving, changing distance and changing angle relative to the Sun and Earth. Even when a feature is real, it may not describe the bulk of the object. It may describe a thin surface layer, a cloud of dust, or a small amount of gas excited by sunlight. The sample's claim matters because nickel is not a typical headline element for comet spectroscopy in simple public narratives. When nickel appears in discussions of small bodies, it often comes with iron, and both are associated with metal-rich material. In solar system history, nickel and iron are also associated with differentiated bodies, objects that once melted internally, so heavier material sank and lighter material rose, producing cores and mantles. That history is familiar from meteorites and from models of early planetary formation, but the sample's insistence is narrower and more provocative. Nickel seems high relative to iron, and that imbalance is treated as a sign of processing. Industrial processing is a strong phrase and cannot be proven from remote spectroscopy alone. Yet the idea gains its power from a simple point. In many natural settings, nickel and iron travel together. If a measurement repeatedly suggests they are not traveling together here, the difference becomes a question that refuses to stay small. A conservative interpretation begins by listing natural routes. One possibility is that the spectrum does not represent the object's composition as a whole, but rather the composition of dust in the coma. Dust grains can be enriched or depleted in certain elements, depending on how they form and how they are heated. Another possibility is that the spectral feature attributed to nickel is blended with other lines, or that the measurement is sensitive to ionized nickel in a way that is not equally sensitive to ionized iron under the same conditions. The excitation of atoms depends on sunlight, temperature, and the density of the surrounding gas. A third possibility is that the object is not comet-like in the usual sense, but is a more rock-like body with an unusual surface, perhaps coated in metal-rich grains from its formation environment. An interstellar origin expands the range of plausible compositions because it is not limited to the solar system's local history. A body formed around another star could have a different mix of elements, a different temperature history, and a different set of materials that survive in the cold. None of this requires engineering. It simply means that interstellar visitors, by definition, may not resemble the comets and asteroids that are familiar. The sample nonetheless keeps returning to the feeling that the nickel point is not merely odd, but pointed, because it sits alongside the motion anomaly. A chemical anomaly alone can be filed under diversity. A motion anomaly alone can be filed under outgassing. Together, they create a compound puzzle, an object that seems compositionally unusual and dynamically unusual at the same time, and that appears to time its approach to Jupiter with unsettling precision. In documentary terms, the chemistry becomes a credibility anchor because it is rooted in an established instrument practice. Major observatories routinely gather spectra of comets and small bodies, and space agencies maintain missions and ground networks that coordinate such campaigns. Even without naming specific papers, it is reasonable to describe how teams would test a nickel claim. They would seek spectra from multiple instruments with different detectors and different wavelength coverage. They would compare observations taken at different times to see whether the nickel feature strengthens or fades, and whether it correlates with brightening that would suggest active outgassing. They would look for companion features that should accompany nickel if the interpretation is correct, and they would check whether iron features are present but weak or absent altogether. They would also compare the object's spectrum with known classes of meteorites and with the spectra of metal-rich asteroids. not to label it, but to see whether the pattern resembles anything in the solar system.
If the nickel signal is robust, the next question is, what physical state produces it? Nickel on a bare metal surface behaves differently from nickel locked in minerals. Nickel in dust behaves differently from nickel in gas. Nickel in gas suggests that material is being released, which suggests heating, which suggests a volatile process, even if the object is not a classic icy comet. This is where the sample's idea of disguised propulsion quietly enters, not as a declared engine, but as a hypothesis that the outgassing might not be random. A high-efficiency propulsion system disguised as outgassing would still need to expel mass. Any thrust requires momentum exchange. That expelled mass would leave a trace in gas composition and in dust distribution. If a jet were narrow and directed, it could alter motion without producing a large, symmetrical coma. It could also, in principle, produce a spectrum that highlights certain elements if those elements are part of the expelled material or part of the surface being heated. Yet this remains speculative, because nature also produces jets. Comets often have narrow jets emerging from small active patches, and those jets can produce non-gravitational acceleration that is directionally stable if the object's rotation and active region geometry are stable. The difference between natural jets and purposeful thrust would be pattern. Natural jets should correlate with solar heating and should evolve as the object rotates and as the sun angle changes. Purposeful thrust, if it existed, would correlate with navigational need and could persist or change when sunlight-based models say it should not. The documentary keeps the focus on what can be observed. One observable is the light curve. The sample describes a metallic sheen and a cleanliness that seems hard to maintain. Light curves are built from repeated brightness measurements, and they can reveal rotation periods and the presence of tumbling. A smooth, stable light curve can indicate a stable spin state. Sharp glints can indicate facets or regions with higher reflectivity. A dusty, active comet tends to have a coma that blurs those signals, washing out rotation signatures and making the object's brightness more dominated by dust production than by surface reflection. If 3i Atlas shows a light curve with clear rotation features despite being active enough to accelerate, that tension is itself interesting. It suggests either low dust production or an unusual distribution of material. Another observable is color. Dust and gas contribute different colors, and broadband photometry can track changes that might signal shifts in activity. Another observable is the direction of the non-gravitational acceleration. Orbit fits can, in effect, infer the direction of the extra force from the way the residuals behave. If the force points in a direction consistent with a jet that is locked to the sun direction, that leans natural. If it points in a direction that repeatedly anticipates upcoming course needs, that leans odd. The sample wants the listener to feel that nickel is the kind of material one would choose for durability. That is a narrative leap, and the documentary treats it as a possibility rather than a conclusion. Nickel alloys are indeed used in harsh environments because they resist corrosion and retain strength at high temperatures. But those uses do not imply that nickel in space must be a hull. Interstellar space is cold and sparse, and many materials can survive it. The more grounded mystery is simpler. Why does the spectrum, as described in the sample, lean toward nickel in a way that seems out of proportion? And is that signal real and persistent as the object approaches Jupiter? If it is real, then 3i Atlas may be telling a story about formation around another star, about unusual mineralogy, or about a surface that has been altered in a way that does not match familiar comets. If it is not real, then the story reveals something else. How quickly an uncertain spectral hint can harden into a narrative when the motion anomaly already primes the mind to look for engineered explanations. Either way, chemistry becomes the hinge between the physical and the speculative. It is the place where hard instrument practice meets the temptation to interpret. The documentary stays in that narrow space, where a few lines in a spectrum are not proof, but they are not nothing, and where the best way to respect the mystery is to let the measurements lead, and let the implications remain open until the data is strong enough to force a choice. The most practical mystery in the sample is not the idea of a hidden message or a concealed plan. It is the quieter claim that 3i Atlas keeps making small, well-timed corrections, the kind of corrections that remain visible only as tiny discrepancies between where the object should be and where it actually appears. In astronomy, those discrepancies are not treated as drama. They are treated as residuals, the leftover offsets after an orbit has been fit to all available measurements. Residuals are expected because every measurement has noise, every instrument has distortions, and every faint target is hard to centroid precisely. What is not expected is residuals that behave as though a small force is steadily acting on the body,
week after week, in a pattern that stays coherent as the orbit solution improves. When that happens, analysts introduce an additional term, a non-gravitational acceleration. And then they test whether that term reduces the residuals across multiple observation sets. If it does, the model gains predictive power. That predictive power is the core of the sample's concern, because it makes the object's future motion look less like a drifting uncertainty and more like a controlled approach to a specific geometry near Jupiter. The simplest natural explanation is still outgassing. Comets are not inert rocks. They are mixtures of dust and volatile ices. When heated, they vent gas, and gas carries dust outward. The recoil is a real thrust. It can be strong enough to alter an orbit measurably over time, especially for small bodies. Yet the thrust does not need to be large to matter. Over long arcs, a small, sustained push can shift a predicted position by enormous distances. That is why interstellar visitors, which arrive fast and can be observed over months, are sensitive tests of these forces. In a purely natural picture, the direction and strength of the thrust should be connected to sunlight and to the object's rotation. If the active region is on one side, the thrust should modulate with the spin, and the net effect should evolve as the sun angle changes along the orbit. The sample implies something different. It implies a net push that behaves less like a thermal response and more like steering, appearing when needed and holding long enough to place the object on a narrow corridor into Jupiter's domain. This is where a documentary approach has to separate what is measurable from what is interpretive. Orbit fits can infer an extra force, but they do not identify the mechanism. They tell observers that gravity alone is insufficient, not why. The mechanism has to be tested against other evidence. If outgassing is responsible, there should be signs. A comet's coma and tail are not decorative. They are mass leaving the body. If enough mass leaves to alter motion, it should usually leave a detectable imprint in brightness, in dust distribution, or in the spectrum of gas. It might be subtle if the jets are narrow, or if the gas is hard to detect at the wavelengths being monitored, but over time, the signatures should correlate. An episode of increased acceleration should have a counterpart in increased activity, or at least a change in the coma's shape. The sample's tension comes from the implication that the acceleration is present without the expected display, as if the thrust is efficient and quiet. That possibility cannot be ruled out on the basis of feeling alone. Comet activity can be gas-rich and dust-poor. A body can vent mostly invisible gas, producing thrust without a thick dust coma. A body can also vent episodically, with brief events that alter motion while leaving only faint traces that could be missed if no telescope is watching at that moment. The question becomes whether the observational record supports such a pattern, especially after the object has passed its closest approach to the sun and moved into regions where ordinary solar heating becomes weaker. If the push persists or intensifies farther out, that does not automatically mean artificial propulsion, but it does make the thermal explanation more demanding. It requires unusually volatile materials, unusual insulation, or a surface geometry that keeps certain regions active longer than expected. The sample uses this to sharpen the feeling of intention, because a sustained, coherent acceleration can behave like planning even when it is natural. There are other natural influences, and they matter because they can mimic thrust in the orbit fit if not accounted for. Solar radiation pressure, the momentum carried by sunlight, can push small, low-mass objects. For a body with an extremely low density or an unusually large surface area relative to mass, radiation pressure becomes significant. That effect depends on the object's shape, reflectivity, and orientation, and it can produce a steady acceleration away from the sun. Interstellar visitors have revived discussion of this effect because it offers a non-outgassing path to non-gravitational motion. But it also demands specific physical properties that may or may not fit what is observed. If 3i Atlas shows a light curve consistent with a compact rotating body, and if it shows dust or gas in a way that suggests a conventional nucleus, radiation pressure becomes less compelling. If it shows unusually high reflectivity and weak outgassing, radiation pressure becomes more plausible. Fragmentation is another influence. If the object sheds pieces, the center of light used for astrometry can shift. That shift can masquerade as acceleration. Fragmentation can also expose fresh ice, changing activity in a way that looks like a new control input. The sample leans toward the idea that the object is too clean and too stable for that. But stability itself needs measurement. A steady light curve could indicate a stable spin state, yet it could also hide slow tumbling if the viewing geometry masks it. The documentary stance holds the uncertainty without flattening the intrigue. The deeper issue
is the timing. The sample claims that the object's corrections have meaning because they line up with a mid-March encounter window near Jupiter, not merely with the Sun's heating curve. This is a testable distinction. Analysts can model expected outgassing forces as a function of heliocentric distance and compare them with the inferred acceleration. They can also fit the direction of the acceleration in space.
Outgassing tends to produce acceleration components aligned with or related to the sun direction because sunlight drives the venting. A force aligned instead with the object's velocity relative to Jupiter at key moments would be harder to explain as simple outgassing. The challenge is that the direction inference is only as good as the data and as the model assumptions. A sparse dataset can allow multiple solutions. A dense dataset from many observatories tightens the result. This is why the sample's concern about limited, high-resolution imagery becomes part of the scientific story, even without assuming motive. Without shared, high-quality observations, the space of plausible natural mechanisms stays large, and the space of speculative mechanisms grows with it. In the background, real institutions provide the scaffolding. NASA and ESA coordinate observation campaigns for unusual objects because early characterization guides later resource allocation. Large survey telescopes provide the discovery and the long arc tracking. Follow-up observatories provide spectra and light curves. Space missions already in the Jovian system, such as long-running orbiters, are not designed to chase a fast visitor, but they can contribute context about the environment and can sometimes participate indirectly through coordinated timing and geometry. The key point is that this is not a mystery that lives only in one data set. It lives in the interplay between astrometry, photometry, spectroscopy, and the evolving orbit solution. The sample treats the corrections as if they are whispers of navigation. A careful documentary voice treats them as a pattern that might become clearer with time. If the pattern resolves into ordinary comet behavior, the story becomes one of an interstellar object with unusual materials and a complex thermal response. If the pattern refuses to resolve, if the corrections remain coherent while the usual indicators do not match, then the anomaly becomes less about one surprising measurement and more about consistency across independent methods. That is where the suspense becomes quiet but relentless, because an object does not need to shout to alter its fate. It only needs to push at the right times, in the right directions, long enough that gravity does not have the final word. Jupiter's irregular moons occupy a different kind of space than the famous inner worlds. Io and Europa announce themselves with size, brightness, and constant attention. The irregular moons are smaller, dimmer, and farther out, and many of them move on tilted, elongated paths that do not match the neat, almost planar architecture of the major satellites. Their orbits suggest capture, not formation in place. In the sample, the Ananke group is singled out as the destination that makes the approach of 3I Atlas feel less like a pass and more like a deliberate entry into a specific neighborhood. The Ananke group is one of several clusters of retrograde moons, meaning they orbit Jupiter in the opposite direction of Jupiter's rotation. Retrograde orbits are not rare in the outer reaches of giant planets, but they are dynamically distinctive. They hint at bodies that arrive from elsewhere and become trapped, either intact or as fragments of a larger object that broke apart after capture. That origin story is mainstream and natural. Yet the sample treats the group's obscurity as an opening for a different interpretation, a place where unusual objects can exist with minimal scrutiny. The obscurity is real in a practical sense. These moons are small, often only a few kilometers across, and they sit far from Jupiter, where sunlight is weak and reflected light is faint. Imaging them sharply from Earth is difficult. Jupiter itself is bright and can flood nearby fields with glare, and the moons move against star backgrounds, requiring careful tracking. Space telescopes can help, and large ground-based observatories with adaptive optics can sometimes resolve more detail, but the observational record is still thin compared with that of the inner moons. A thin record does not imply concealment. It implies a straightforward limit. Time on powerful instruments is scarce, and many targets compete for it. Yet scarcity of imagery has a side effect that the sample exploits. In regions with limited data, unusual claims are harder to settle quickly, and speculation can thrive because it is not immediately pinned down by a single decisive picture. In a documentary frame, the Ananke group becomes important for a more grounded reason. It is not just a set of faint points, it is a moving gravitational environment. If 3I Atlas truly passes into Jupiter's outer system and comes near one of these moons, the encounter is not merely symbolic. It can measurably alter the visitor's trajectory. Even a small moon has gravity. At close range, that gravity can bend a path, and in a three-body interaction with Jupiter and the Sun, that bend can shift energy. The magnitude depends on approach distance, relative speed, and geometry, but the principle is solid. A close pass near a small irregular moon, especially in the days after the visitor crosses into Jupiter's domain, is a plausible place for the energy bookkeeping of capture to change. This is why the sample's focus on a particular moon matters. The claim is not that 3i Atlas drifts through a random swarm. It is that it approaches a named, small target in a defined cluster at a defined time. That makes the Ananke group a stage for a test. If the visitor's track shows a gravitational kink consistent with a near pass, and if the post-encounter orbit shifts toward binding, then the group is not simply scenery. It is part of the mechanism. The retrograde nature of the group adds another layer. Retrograde encounters can produce high relative speeds, reducing the duration of a close pass. Short encounters generally limit how much gravity can reshape energy, which makes successful capture less likely through a single, clean encounter. That constraint does not forbid capture, but it demands a more specific alignment or an additional energy loss channel. The sample uses this constraint to sharpen suspicion. If capture looks possible despite the odds, then something else might be acting. A documentary voice keeps the logic but avoids the leap. The constraint simply raises the bar for natural explanations. It does not remove them. Multiple encounters are possible. A visitor can pass near Jupiter, loop through parts of the system, and experience repeated gravitational interactions with moons over time, especially in cases of temporary capture. Those repeated interactions can gradually change the orbit without any engine. They also complicate the narrative because they blur the line between an event that looks like a single rendezvous and a sequence of near misses that happen to occur in the same neighborhood. The sample also hints at orbital synchronization, describing a timing in which the small moon reaches a distant point in its orbit earlier in the year, as if moving into place for a meeting. Synchronization can happen naturally. Orbits have periods. When many bodies move through space on predictable cycles, alignments occur. Some alignments are rare, some are common, and human attention tends to notice the rare ones more strongly. The question is whether the alignment is truly rare given the full set of possible moons and encounter geometries, or whether it becomes rare only after the story chooses one particular target. This is where careful framing matters. Jupiter has many irregular moons. A visitor passing through Jupiter's outer region will, by chance alone, have some closest approach to some moon at some time. The sample's power comes from specifying a narrow candidate encounter and implying that the visitor's earlier non-gravitational acceleration serves that outcome. If the visitor's trajectory, after accounting for ordinary uncertainties, continues to predict that same close pass and continues to do so as new data arrives, then the coincidence argument weakens. If the prediction shifts between targets or distances as the fit evolves, then the sense of a chosen destination may be an artifact of early uncertainty. The documentary tone treats the Ananke group as a diagnostic rather than a verdict. It is the part of Jupiter's system where ordinary data is sparse and orbital dynamics are complex. So it is also where an interstellar visitor can appear most uncanny. The sample amplifies this by noting how few clear images exist. That absence shapes public perception, but it also shapes scientific caution. When direct imaging is weak, analysts lean harder on indirect signatures: the visitor's astrometry, the inferred acceleration, the timing of brightness changes, and the subtle shifts that reveal whether gravity alone can account for the track. The irregular moons are also useful for another reason. Their orbital orientations and inclinations are distinctive enough that a close approach is not easily confused with another. If 3i Atlas passes near a retrograde moon, the geometry is not generic. It carries a signature in the relative motion that can be modeled and checked. This turns the story from an abstract fear of hidden objects into a concrete measurement problem. Does the visitor's path intersect the predicted location of that moon within the stated uncertainties? And does the visitor's motion afterward reflect the gravitational influence expected from that encounter? If the answers align, the Ananke group becomes less mysterious in one way and more mysterious in another. It becomes a place where a rare sequence of natural events might be unfolding in plain view, while the lack of imagery prevents quick closure. If the answers do not align, the group still matters because it reveals how easily the mind turns obscurity into intent. The sample also frames the Ananke group as a region no one is looking at, but in reality, astronomers do look, though not with the frequency reserved for brighter targets. Survey telescopes cover large areas of sky repeatedly, and their archives can be searched for faint motion. Dedicated follow-up can be scheduled when a target becomes important. The limiting factor is not indifference, it is capacity. This is why the mid-March window is so consequential. It provides a reason to concentrate that capacity. If the claim is a close pass near an irregular moon, then an observing campaign can be designed around it, aiming to capture high-cadence astrometry and spectra during the days when the encounter influence should be strongest. Even without a clear image of the moon itself, the visitor's motion can betray the encounter. The Ananke group, in this frame, is not merely a cluster of neglected rocks.
It is the region where a fast visitor meets the solar system's most irregular architecture, and where small deviation can decide whether the visitor leaves again or begins to circle. The sample suggests that this neighborhood is chosen because it is quiet. The documentary does not need that motive to sustain intrigue. The quiet is already real, and in that quiet, measurements carry more weight than images, and small forces can masquerade as deliberate choices until the orbit either closes into captivity or opens into escape. The sample's most specific claim is also the easiest to test in principle. A close pass in mid-March 2026 between 3I Atlas and a tiny irregular moon in Jupiter's retrograde population, occurring shortly after the visitor crosses into the zone where Jovian gravity begins to dominate locally. This is the point where the story stops being about general oddness and becomes about a particular meeting in a particular place at a particular time. In scientific terms, it becomes an ephemeris problem. An ephemeris is a schedule of positions, a prediction of where an object will be on the sky at given times. For 3I Atlas, the ephemeris is refined as new astrometric measurements arrive. For the irregular moons, ephemerides exist as well, built from decades of tracking and continual orbit updates. The moons are faint, but they are not unknown in the mathematical sense. Their paths are stable enough to predict where they will be, even if they remain unresolved points. When the sample frames the encounter as a close pass to a body only a few kilometers wide, it is relying on this difference between seeing and predicting. A meeting does not require a close-up photograph to be real. It requires the trajectories to overlap within their uncertainty ranges, and it requires the visitor's motion afterward to reflect the gravitational influence expected from that proximity. This is where the claim becomes sharp. If the visitor's fitted orbit continues to predict the approach as the date draws near, and if independent teams using independent datasets converge on the same window, then the event is not a loose, poetic idea. It is a defined, dynamical encounter. The sample emphasizes the strangeness of choosing such a target because the target is small, retrograde, and not part of the high-profile inner system. From the standpoint of probability, that emphasis can cut two ways. Jupiter's outer system contains many irregular moons on a variety of inclinations and distances, and any visitor passing through that region will, by definition, have some closest approach to some moon. That is the background chance against which any claimed rendezvous must be measured. The reason the sample treats this one as different is that it ties the close pass to earlier anomalies, especially non-gravitational acceleration and apparent microcorrections after the object passes the sun. In that framing, the close pass is not an incidental nearest neighbor. It is the endpoint of a series of adjustments. A conservative scientific approach asks whether the adjustments are actually required to reach the encounter corridor. Orbit analysts can test this by fitting models with and without non-gravitational terms and comparing the predicted closest approach distance to the moon. If purely gravitational fits predict a wide miss, and the inclusion of non-gravitational acceleration narrows the miss toward a close pass, then the data is indeed suggesting that the extra force matters for the encounter geometry. That still does not establish intent, but it establishes dependence, and dependence is the part of the claim that can be measured. The sample adds a timing detail that intensifies the feeling of coordination. The moon's earlier position in its orbit, described as reaching a distant point as if moving into place. Orbital timing can look eerie because it is precise by nature. Each moon repeats its cycle. Alignments occur because cycles overlap. The correct question is not whether the alignment looks neat, but whether it is unusually rare given the full set of moons that could have served as a near-pass target. That is a hard question for casual audiences, because it requires considering alternatives that the narrative does not foreground. It is also a question that scientists can, in principle, answer by simulation. One can take the visitor's incoming trajectory, sample within the uncertainty range, propagate it through the Jovian system under gravity, and compute closest approaches to the known irregular moons. If many similar close approaches appear in the distribution, the specific encounter is less special.
If the distribution shows that close approaches at this level are rare and the named moon stands out as a unique low-distance event, the encounter gains weight. The sample's choice of a retrograde group remains important because retrograde motion typically increases encounter speeds. Higher relative speed compresses the interaction time, which reduces the ability of a small moon to trade meaningful energy with a fast visitor. That constraint is not an opinion. It follows from the geometry of motion.
The faster the pass, the less time gravity has to curve the path, and the smaller the gravitational deflection for a given closest distance. This makes the sample's implied outcome, capture into a stable orbit, harder to achieve through the moon alone. The consequence is not that capture becomes impossible, but that capture would then require either an extremely close pass, an additional gravitational sequence involving Jupiter itself and perhaps other moons, or a non-gravitational force that removes energy in the right direction at the right moment. This is why the rendezvous claim is so central. A close pass to a small moon becomes the hinge where the story can move from steering to braking. If the visitor remains unbound after the pass, the encounter can be chalked up as a close approach that happened to occur in a crowded system. If the visitor's energy relative to Jupiter drops noticeably, then the question of mechanism becomes unavoidable. The sample hints at the visitor entering a stable orbit with the moon, or at least joining the retrograde neighborhood. In strict dynamical terms, joining a group is not as simple as being nearby. The group shares orbital characteristics, but each moon has its own orbit. For the visitor to be placed into a similar retrograde orbit, it would need a very particular angular momentum change. Gravity can change angular momentum in flybys, and three-body exchanges can do surprising things. But large changes are less likely without a close, energetic interaction. Non-gravitational acceleration could also change the orbit, but again, it must point in a direction that supports the required change, rather than simply producing a small radial push. This is where the best observational strategy becomes clear. During the days around the predicted close pass, high-cadence astrometry can reveal whether the visitor's path shows a deflection consistent with the moon's gravity. That deflection may be subtle, but with enough precision, it can be detected as a deviation from the pre-encounter orbit solution. At the same time, photometry can watch for sudden changes in brightness that might signal outgassing bursts, fragmentation, or changes in rotation state. Spectroscopy can look for transient gas features that would accompany any sudden activity, especially if the outflow composition includes unusual elements. If the sample's nickel hint has substance, this window is when it might sharpen, either because activity increases or because geometry improves. If the sample's claim of quiet corrections is accurate, this window is also when a correction would be most consequential, because the direction of thrust relative to Jupiter at closest passage would have the largest effect on whether the object leaves or stays. A subtle push at the wrong time might only move the track on the sky. A subtle push at the right time might change the visitor's fate. The sample also implies that high-resolution imagery is limited or withheld, which feeds the sense of a controlled narrative. A documentary approach does not need to endorse that implication to acknowledge its effect. Limited imagery, for any reason, shifts attention toward orbit solutions and indirect inference. It also raises the value of independent observation campaigns. If multiple observatories across the world, using different instruments and different reduction pipelines, report consistent astrometry through the encounter window, then the orbit change, if it occurs, becomes difficult to attribute to a single systematic error. If different teams report different results, then uncertainty grows, and the story becomes about the limits of measurement at the edge of what can be tracked. The rendezvous claim is therefore a catalyst. It forces the conversation away from vague suspicion and toward a measurable moment. Either the predicted close pass occurs at the predicted time within uncertainty, or it does not. Either the visitor's post-encounter path shows a significant energy change relative to Jupiter, or it does not. Either any non-gravitational acceleration correlates with physical activity indicators, or it resists those correlations. The sample treats the coming moment as a handoff. The documentary treats it as a fork in the data. If the fork points toward ordinary dynamics, the mystery becomes one of interpretation and human expectation. If the fork points toward capture or an unexplained energy loss, the mystery becomes physical, and the question shifts from what observers believe to what the object demonstrably does. In the sample, the physical anomalies of 3I Atlas are paired with a procedural anomaly, the feeling that the data itself is being treated differently from the data of ordinary comets.
That is a powerful pairing because it shifts the mystery from the object alone to the human systems that observe it. It also demands caution because procedural claims are easy to make and hard to verify without access to internal channels. Still, the sample's emphasis is worth examining in the plainest terms, not as proof of anything, but as a way to understand how uncertainty grows when information is unevenly shared. In astronomy, information moves through several layers before it reaches the public. The first layer is raw observation, images and spectra recorded by instruments. The second layer is reduction, the process of correcting those raw files for distortions, background noise, and calibration so that positions, brightness, and spectral features can be measured. The third layer is analysis, the fitting of orbits, the extraction of composition hints, the modeling of non-gravitational forces. The fourth layer is communication, where teams decide what to release quickly, what to hold for verification, and what to submit through formal channels. Delays happen for ordinary reasons. Telescope time is scheduled, data pipelines take time, and cautious teams do not rush claims that can be overturned by a better calibration or a longer observation arc. The sample suggests something sharper than delay. It suggests classification, restricted handling, and protocols associated with a year that carries cultural weight. The year named is 1947, and the sample links it to secrecy practices associated with early Cold War intelligence and to the enduring mythology of unexplained aerial events. Even if the claim is uncertain, the effect is clear. Mentioning a historically charged year makes the handling itself feel like a signal. A calm documentary approach treats the claim as unconfirmed while exploring what forms of restriction can exist in real practice. Some data in astronomy is proprietary for a period because a team has earned it through a proposal and is given time to publish. That can look like withholding from the outside, even though it is routine. Some data can be limited because it comes from instruments or networks that are dual use, serving both civilian science and other monitoring tasks. Some information about observation schedules can be less transparent for security reasons, even if the scientific product eventually appears. There can also be restrictions when the object of interest is close to Earth or relevant to planetary defense, because coordination involves national agencies and public messaging. None of these cases require a dramatic hidden truth. They require only institutional caution.
Yet the sample insists on a particular flavor of restriction, the idea that high-resolution imagery is being classified and that orbital coordinates are being redacted under older protocols. Those are specific claims. If they were true, they would represent a departure from ordinary scientific practice because orbital elements for comets and asteroids are usually published openly through standard services precisely so that independent observers can track them. Redaction of an orbit would be unusual because it would prevent verification, and verification is the core immune system of astronomy. The documentary voice, therefore, holds two competing realities at once. The first is that faint targets near Jupiter can be hard to image, and the lack of clear pictures can be explained by technical limits rather than secrecy. The second is that the mere perception of restriction, whether accurate or not, changes the way anomalies are interpreted. When the public sees incomplete data, it fills gaps. When it hears that something is classified, it assumes that what is missing is more important than what is shown. This is not a psychological lecture. It is simply the predictable behavior of any information environment where the object is already framed as unnatural. In the sample, the procedural anomaly amplifies the physical anomalies: non-gravitational acceleration, unusual composition hints, precise timing toward a retrograde moon. Together, they create the sense of a coordinated narrative where the object navigates and the institutions respond by narrowing visibility. A documentary frame keeps attention on what can be checked without access to classified systems. One check is consistency across independent sources. If orbital solutions from public astrometry continue to converge, and if they continue to predict the same mid-March geometry, then the event does not depend on private channels. It exists in the open sky. If orbit solutions are scarce or inconsistent, then the perception of restriction is partly created by a simple lack of reporting, which can happen if few observatories are following the target closely, or if the object's faintness makes measurement difficult. Another check is the behavior of the scientific community. When an object becomes genuinely important, informal coordination often appears: circulars, alerts, and a rise in follow-up reports. If those signs are absent, it might mean suppression, but it might also mean that the object is not behaving as dramatically as the sample implies, or that the predicted window has not yet triggered intense attention. The sample implies silence,
And silence is hard to interpret because it can signal caution, disinterest, uncertainty, or limited capacity. Still, silence becomes part of the story when the claimed event is as dramatic as a potential new Jovian moon from another star. The most grounded way to treat this secrecy aura is to ask how classification would interact with actual measurement. Classification could limit the release of high-resolution imagery, but it would struggle to erase the object's motion from the sky. Independent observers can track a moving point of light. They can report positions. They can build their own orbit fits. That is why, historically, attempts to control astronomical narratives tend to focus on interpretation rather than observation. Controlling interpretation is easier. It involves selective emphasis, cautious language, delayed publication, and the framing of anomalies as uncertainties until they fade from attention. The sample treats the official narrative as dry and textbook-like, and that dryness is itself portrayed as suspicious because it seems misaligned with the object's behavior. A documentary voice treats dryness as a real institutional style. Agencies and observatories tend to speak carefully, especially about unusual claims. They avoid language that implies intent. They avoid overstating early results. They sometimes choose the most conservative natural explanation, even when it does not fit perfectly, because conservative explanations can be revised later without damaging credibility. This practice can look like denial from the outside, but it is also how scientific institutions protect themselves against sensational misinterpretation. The sample's metaphor of an ordinary object being misnamed is replaced here by a simpler contrast. A system that moves slowly and cautiously meets an event that, if real, moves quickly and forces decisions. The tension between those speeds can feel like concealment, even when it is only caution. Yet, the sample also points to a particular kind of caution, one tied to national security rather than academic restraint. That possibility cannot be dismissed out of hand in a world where surveillance networks exist and where unusual objects can intersect with defense concerns. If an interstellar object were suspected, even weakly, of being technological, the consequences would extend beyond astronomy. Agencies would become involved. Access would narrow. Communication would become controlled. This remains speculative, but it is the speculative space that the sample invites, and it is grounded in a realistic institutional response to uncertainty combined with perceived risk. The documentary voice keeps the distinction clear. There is a difference between what is claimed about protocols and what is publicly observable in the object's motion and spectra. The most important outcome does not depend on internal memos. It depends on the orbit after the Jupiter encounter. If 3i Atlas remains bound, the sky itself will reveal that truth over time, because a bound object returns. If it departs, the capture claim weakens, regardless of the handling narrative. The secrecy aura therefore functions as an accelerant, rather than an engine. It makes the mystery feel larger, but it cannot substitute for the energy accounting that orbital dynamics demands. If the mid-March window brings an orbit change that cannot be explained by ordinary mechanisms, then procedural restriction becomes more consequential, because it would limit the ability of independent observers to test competing explanations. If the mid-March window resolves into an ordinary flyby, then the secrecy aura becomes a lesson in how easily restricted visibility can reshape perception, even when the underlying event is less extreme. In the sample, the fear is not only that the object is unusual, but that the response to it is to keep it at the edge of clarity. The documentary frame holds that fear as a hypothesis. The coming measurements and the openness of those measurements across independent channels will decide whether the atmosphere of secrecy is a shadow cast by limited data or an additional anomaly that demands explanation in its own right. As mid-March 2026 arrives, the story becomes less about interpretation and more about what an orbit does when it is forced into a narrow corridor of outcomes. 3i Atlas either leaves Jupiter behind on an open track back to interstellar space, or it begins to behave like something bound to Jupiter for at least a time. Between those extremes lie temporary captures, looping passages that can last weeks or months before the object escapes. And those intermediate cases are important because they can look like an arrival without becoming a permanent new moon. The sample treats the moment as the birth of a 96th moon, a new entry on the map, a body that was not there yesterday and then is there today. In practice, recognition of a new moon is not instantaneous. It depends on repeated observation, on confirming that the object's motion is Jupiter-centered, and on ruling out a transient track that merely resembles capture. But the core idea remains. If the object's energy relative to Jupiter decreases enough that the path closes, something has changed in a way that gravity alone struggles to produce for a fast interstellar visitor. This is where the documentary must keep its calm and let the physics do the heavy lifting. A bound orbit is a repeated promise. It brings the object back. It makes prediction easier, not harder. If 3I Atlas becomes bound, observers will not have just a single close pass to argue about. They will have a sequence of returns. Each return will allow improved astrometry, improved spectra, improved light curves, and the slow accumulation of physical facts. The mystery would not end, but it would change shape. It would move from a race against a departing target to a long investigation of a resident. That transition is what makes the sample's tension feel so high, because it imagines a one-time visitor transforming into a permanent presence.
Yet the same transition also undermines the need for secrecy narratives, because an object that remains cannot be hidden easily. The sky itself becomes a record. If the object departs, the opposite happens. The window closes. The object fades. The data becomes historical rather than current, and interpretation hardens because new tests become harder to perform. That is why the sample's insistence on urgency feels natural, even in a restrained voice. A transient target forces decisions before the evidence is complete. The scientific heart of the moment is still energy accounting. If capture is claimed, the change in orbital energy can be estimated from the pre-encounter and post-encounter trajectories. Analysts can compute the object's speed relative to Jupiter before closest approach and after, and from that infer the scale of the energy loss needed. They can then compare that energy loss with what is plausible through known mechanisms. A three-body exchange with a moon can, in principle, produce an energy change, but the magnitude depends on how close the pass is and how the geometry aligns. A close pass to a tiny retrograde moon, as framed in the sample, is a difficult route because relative speeds are high and interaction times are short. If the measured energy change is small, a natural exchange might suffice, especially if the encounter is extremely close or if Jupiter's own gravity and the Sun's pull combine to create a temporary trap. If the measured energy change is large, a single moon encounter becomes less plausible. Then attention shifts to other possibilities, a sequence of interactions rather than one, a fragmentation event that changes the effective orbit solution, or a non-gravitational force acting during the encounter window in a direction that removes speed. If that last case is supported by the data, the story tightens around a question that is simple to ask and hard to answer. What force acts in deep space that can be tuned with the right timing and direction? The sample's earlier anchors re-enter here as constraints rather than decorations. The light curve matters because a stable rotation can support stable jet geometry, which can support a coherent non-gravitational acceleration. The spectrum matters because if mass is being expelled to produce thrust, the expelled mass should leave chemical signatures. The reported nickel hint matters because if it is real, it may point to an object with unusual material properties that change how it vents or reflects. The secrecy aura matters because if competing interpretations arise, public confidence depends on access to the same underlying observations. The documentary voice does not need to decide which interpretation is true at this moment. It needs to show what each interpretation must explain. A purely natural picture must explain a fast interstellar visitor that appears to slow enough to linger near Jupiter while showing minimal or unusual signs of activity, and while aligning with a close pass near a small retrograde moon. A propulsion picture must explain how thrust is produced without obvious plumes, how it remains hidden while still altering motion, and why the object chooses the most obscure region of the Jovian system rather than a more direct or more stable approach. A mixed picture must explain how ordinary comet forces could be amplified or directed by unusual structure, perhaps by vents that open and close, by insulating layers that store heat, or by a surface that interacts with sunlight in a way that produces sustained recoil without much dust. Each picture has vulnerabilities. The documentary remains honest about that. What it adds, without exaggeration, is a sense of how rare it is for the solar system to offer a moment where the question can be posed so cleanly. Interstellar visitors are rare. Close encounters with Jupiter's irregular moons are rarer still. A possible capture event is rarer than that. The rarity does not prove intent, but it does raise the stakes for interpretation because rare events are where models are tested at their edges. If 3I Atlas behaves like a standard comet with odd composition, it teaches about diversity in other planetary systems. If it behaves like a body responding to forces not easily explained by sunlight and ice, it teaches that the catalog of small body behavior is incomplete. If it behaves like something that can regulate its own motion near Jupiter, the teaching would be deeper and more disturbing, not because it confirms a specific narrative, but because it would imply that the difference between natural and artificial is not always obvious in the data, and that the solar system's quiet can contain motions that look like choice. The sample ends with the idea that the silence of space is about to be broken. The documentary ends more carefully because silence can break in many ways. A comet can surprise. A measurement can be wrong. A model can fail. An object can be stranger than expected without being engineered. The open question at the end of this encounter is therefore narrow and sharp. After the mid-March passage, does 3I Atlas return to Jupiter's sky as a repeating, bound body, or does it recede into the dark on a path that never loops back? If it returns, what removes the energy that should have carried it away? If it departs, why did the approach align so closely with a corridor into the least observed region of the Jovian system? And why did the residuals and chemical hints line up in a way that made a drifting rock feel like a visitor with a plan? The answer, if it arrives at all, will arrive not as a message, but as a set of numbers that continue to agree with one another night after night, until coincidence either collapses into mechanism or expands into something that the current language of comet science cannot fully hold.